All right, team, this is for the force due to a magnetic field, and this video will help you understand how to do problems with the force due to a magnetic field. First, understanding that the force due to a magnetic field is the cross product of multiplying the charge multiplied by the cross product of the magnetic field. So velocity, magnetic field. It means that as a particle is traversing somewhere in a certain direction, if there is a magnitude, or not a magnitude, a magnetic field acting perpendicular to this force or to this velocity, there's going to be a force also acting on this particle. Now, the particle itself, the direction of the force itself, it has to do with the cross product, right? So that's why I have a little right hand right here. This is a right hand that I have here. And this right hand, we can write down that this is V, the direction of V, using the index finger. And this is the magnetic field. So index finger, middle finger is the magnetic field. Notice how the middle finger is bent, so we create a 90-degree angle with our index finger that is pointing straight out. This cross product, or this multiplication of cross product, creates the force. And that is the direction of our force. There is one caveat to this. This is true for all positive charges. All positive charges. However, if you are dealing with a negative charge, you would do the same process, except now, once you raise your thumb and you realize that it is a negative charge, then this force will actually be going the opposite way because it is a negative charge. So let's do these problems or this system one at a time, so we can go through it together. Okay. So first, do me a favor and put your right finger, directly downwards into the page. Okay? Or downwards, not into the page, but downwards. Okay? Now, this little dot right here means that the magnetic field is going out of the page. So, straight finger downwards, the index finger downwards, then the magnetic field, which is your middle finger, is going out of the page, out of the screen. And now, because it is going out of the screen, see where your thumb is located at. And if your thumb is located at where this force is at, right here, then you are doing it correctly. Let's do this one, and then I'll cut to D. Okay, so for B, point your index finger, your first finger, straight up. And then put your magnetic field finger, which is this one, magnetic field finger, which is your middle finger, towards the, I'm doing it myself now, towards the right. Now, notice where your thumb is pointing at. It should be pointing into the screen. So you're going to be, okay, into the screen, done. So that means that your force is going into the screen. And this is because, just remember, this is a positive charge. If it was a negative charge, then your forces would have been an opposite. And this would have been a dot, meaning it's coming out. but it is a positive charge, so it continues doing that. So this one, D, is a little bit different because if you try to do it with your thumbs, you're going to bend yourself. It's not possible. It is, you need a cross product, meaning that you need the perpendicular vectors, and because you don't have perpendicular vectors in this scenario, and it is completely parallel to each other, force is equal to 0 in this one. So let me know if this was helpful for you to understand the actual maneuvers. I have this diagram here to help you out, and let me see. Say for example, in this scenario right here, this is actually perfect because for this one, velocity is pointing downwards, right? B is pointing out of the page, and then force right here is pointing towards the left. This is actually pretty neat. Okay, now let's go to another problem. Let's go to 11-27. I'm going all the way to the end. (11-27). So I want to talk about this problem because it has to do with the magnetic fields in a particle. And let's say it's saying that an oxygen ion, and you don't have to worry about this. You don't have to worry like, ooh, what is this actually? The only thing you have to worry about is the mass that they give you, the velocity, the radius, and the magnetic field. Okay, so it says what positive charge is on the ion. If we write the equation immediately when we're looking at this and we're looking at magnetic field, which should be the magnetic field, mass, velocity, and radius. Okay, so this is actually a force due to magnetic field, and I'll show you how the radius and the mass fall into place. Okay, so we Q velocity cross product of B. So this means that I have the magnetic field, velocity, and charge. So how do I visualize this? Well, it says that a velocity of a particle with a certain velocity is traveling perpendicular to the magnetic field. That should be the first hint that you have to use the force to the magnetic field. Okay? If you want to draw it out, we can definitely draw it out. Just remember that the key is perpendicular to the magnetic field. Velocity is perpendicular to the magnetic field. So it doesn't matter how you draw it, just as long both vectors are perpendicular to each other. Okay? So let's do it where we have a particle that is traveling, let me lower it down, particle right here that is traveling at a certain speed that we know, which is 5.10 to the 6, and the magnetic field in which this particle is traveling through, the particle is experiencing a magnetic field that is going into the page. Okay? So this is still acting, the magnetic field is still acting perpendicular to the velocity of the particle. But if we do the right-hand rule that we taught you, where is the force acting on now? So let's do it. Let's point out the finger. Let's put the finger, the index finger, your first finger straight ahead, or straight to the right of the page. Now point your middle finger into the screen, because that is where your magnetic field is at. And it should be that the force acting on the particle is actually acting, let me erase this, is actually acting upwards. Okay? The particle is being pushed upwards, and every time that it starts moving, or every time that it moves, it is a continuous push towards this direction. So I'm going to grab this and just imagine it just moving this way now, and then, oof, okay, that didn't work as planned. Let me just go backtrack, just do this again. So every time that it moves, the force continues to act towards the center, and continues and does a full circle, and it stays stuck in that circle. Because it stays stuck in that circle and the force is constantly pointing into the circle, it means that if I were to analyze the centripetal force of this system, it would equal to the force due to the magnetic field, because both of them have the same equality in terms of force. So we have force of the magnetic field equals the centripetal force. We rewrite this as QV cross product of B, or cross product of the magnetic field, equals mass times centripetal acceleration, because centripetal acceleration is the radial acceleration, the acceleration that goes into the page, or into the circle, into the circle. Okay, so QV, and let me erase this. The reason why now this is going to be a little bit simpler is because QVB turns into sine of theta. That's what happens when you multiply two cross products. You have to multiply, once you do it, once you get the cross product away, the thing that it helps is multiplying by the sine of theta. So QVB is actually equal to Q cross product of B. The thing is that the angle in between these two is already 90 degrees. The sine of theta helps when the vectors are not completely 90 degrees, and it does the analysis to actually get the value of the force of the magnetic field, using sine of theta. Okay. So we have QVB sine of 90, because it's already 90 degrees, and that turns into 1, and then mass times velocity square over r. So where did I get this? If I go to my PRC, I'm going to look at this equation right here, which is the radial / centripetal acceleration. Going back to my problem, this, I substitute my radial / centripetal acceleration with v squared over r. Now, all I have to do is solve for the charge. So I bring everything to the other side. Q mass velocity square over r over v b, there we go, and then I cancel the one v, and I am left with mass times velocity over b r, which is magnetic field and distance from the axis of rotation. Okay, and once you plug all those in, you should get some value in Coulomb. Hopefully this was helpful. If for those of you that are interested in just continuing the problem, B it is asking what is the ratio between the charge and the charge of an electron. So you would go charge over and go to your PRC. The charge of an electron is the smallest charge that you can possibly have on a particle. The same way that you would have the charge for a proton, the difference is that the charge of an electron is negative while the charge of a proton is positive. Okay, so the elementary charge is 1.602 times 10 to the negative 19. If you go over here, you just have to divide by that charge to get the ratio in part B. Then C asks, discuss why the ratio found in B should be an integer. And the reason why it should be an integer is because the charge is actually quantized, meaning that the smallest possible charge that you can have is this, 10 to the negative 19 Coulomb, but the more charge you have, it's actually multiplied by an integer. So now we have, let's say that these are 4 electrons right here. So now you have a charge that is equal to 4 electrons, or for 4 protons, or a charge that is equal to 100 times 1.602 times 10 to the negative 19. That is why it is quantized. Whenever you see a charge and it's exponentially bigger, it's actually letting you know that if you divide by this value right here, you can find out how much, like in terms of particles, in terms of protons or electrons, how much charge does that system have? Or electrons have, electrons or protons. Alright, hopefully this video was helpful, and remember to do your right hand rule. Make sure you practice right hand rule. Alright, you got this. Alright. Have a good day, and I may do one last video. I'll think about it.